So, with this, so now you define what is called abstract non-singular curve. So, this abstract non-singular curve is some kind of, so first of all, any non-singular curve is an abstract non-singular curve, but not all abstract non-singular curves are actually comes from non-singular curve, the usual non-singular curve. So, you need, it's kind of enlargement of the category of non-singular curves. Okay. So, you have this set Ck, which is set of all DVRs, right? Containing R, and it's in R is a DVR. On this set, you give the cofinite topology. So, what is the meaning? That means that the closed sets are finite sets. So, topology on so closed sets are finite sets. So, now once you give a topology, you need to define what is called to give a abstract variety structure. You need to say what are the functions or regular functions. So, closed sets are finite sets. So, this is same as saying that open sets are infinite, because this set of all this set is infinite. This is infinite set. This is infinite. This is because of this fact that if I take any curve y, then if we take a point P, then these OYPs are distinct. So, now if you are over algebraically closed field, so the number of points are infinite. So, that will say that number of DVRs are infinite. So, open sets are subsets of Ck whose complement are finite. Now, if you take such open subset, so you take some open subset, then you define O of U. So, for any open subset U, you define OU to be intersection of the DVRs. All DVRs are subset of K. So, intersection makes sense. P belongs to U, right? So, when I mean P means it's this is the indexing set, that every point corresponds to a DVR, a local ring. So, now for any open, say now on Ck you have a topology. Now, U is open subset. So, the topology on Ck will induce a topology of U, right. So, open subsets of U will be those subsets of U whose complement in U is a finite set. So, so on. So this is a sheaf. So define a function on U. Now, so now on U, you define this OU. So if I denote, so this is a structure sheaf. Now, if you take another abstract, so let's call it O1. If you take this is O2, this is the structure shape. O2 is the O restricted to V. Now, you define a map of morphism from, so it's a set map from U to V, so which is a sheaf theoretic map. That means, if we call this U to V phi, then phi hash, this is a map from OV to phi lowest order of U. So, this is the usual way you define variety. So, it takes the regular functions to, so these are called regular functions on U. So, elements of this. So, the continuous map between, so a morphism between abstract non-singular curve is a map phi comma phi hash, where phi takes any regular functions. So, these are regular functions on U. and you can check that if you have a in the sense of, if you take a C1 to C2, in the usual sense of non-singular curve, then this is, or let us say y1 to y2, then y1 will associate, you can associate a abstract non-singular curve, so call it cy1, and this you call it cy2, right. So then this map will be continuous. If this is a morphism, this is a morphism, and vice versa. If this is a morphism of abstract non-singular curve, then this is a morphism. So of course, they are in the function field K. Both y1 and y2 are in the function field K. Okay. So now, now the point is that these regular functions. So this is the I mean you can think this element of this OU as functions on U. I mean so if you take some element AF in U, I mean literally you can think as a function, because you take U, so you define the map U to K. So every point corresponds to the local ring P. So P corresponds to every point here corresponds to this RP. So now from RP to the RP mod MP, you have a map. The MP is the maximal ideal of RP. Then P goes to so if I take any element AF in intersection of RP, this is the element in the OU. So this is your O of U. So now you take the image of AF in RP mod MP. So every point, so you define, so that is the evaluation map. So that's how you think as any element in intersect OU as a function on your open set U. So that's how you can. This is a very scheme. This is the way you think for schemes. You think the element of ring as a function on spec of A. So exactly same idea here. So now, so you have this category. So what I am saying, that this category of non-singular abstract algebraic curve. So you denote it by U and OU, right? So where U is an open subset, where U is an open subset in CK, and OU is the intersection of the DVRs. So like I said, so there's already said that I write it as a proposition that every non-singular quasi-projective curve Y with function field K, K you fix, corresponds to an abstract non-singular curve. CK, curve in CK. Okay. So now the proof is so if you take a non-singular curve, quasi-projective curve Y, so you associate this CY, so that you take point P to OY of P. So this is the map. So this collection. So this CY is nothing but all these OYPs, and you know that if you take P and Q, two different points, they are different. So that will say this these local rings. Okay, and then first step is that this set is cofinite. So that means that this is inside CK, because they are DVRs, and then the complement, so CY complement in CK, this is finite, or this is open subset. So that is same as say the CY is an open subset in CK. So this is the first claim 1. And claim 2 is that this is a morphism of abstract varieties. So this map, if I call this phi, phi is a morphism of algebraic varieties, abstract algebraic varieties, abstract non-singular curves. So I am not going into detail of this proof. You can look at the book of Hartshorne, again chapter 6. So for details, you see proofs of Hartshorne chapter 6, Hartshorne chapter 1, section 6. Okay, so now the point is that now see in the CK, my curves are abstract curves are all open subsets, but there is a one special open set which is the CK itself. So that should correspond to some curve, and that is my candidate. That is my candidate of that projective curve. So CK itself is a abstract non-singular curve, right? The complement is empty, which is finite. So CK itself is a abstract non-singular. So claim is that this CK is a projective curve. Is a non-singular. And this is the unique non-singular curve, projective curve in the each. So remember that if I fix a k over k, then fixing a k, capital K, means that I am fixing a birational class. So once you fix a birational class, this is the unique curve CK, which is lying in this class. So CK is a non-singular projective curve in the usual sense, what is called non-singular projective curve. So the idea of the proof, so proof is that, see what you do, see this CK for, see if you take any non-singular projective non-singular curve, so then this yi will correspond to some cyi, right? So then this is a open subset here. Now the point is that the complement is a finite set. So in that sense that you can cover this CK by this finitely many yi, such that CK is union of CYI. This is because the complement is finite. So if I take some point in some DVR which is outside CYI, then but every DVR comes from a non-singular curve. So I can construct another curve Y2 such that that will the local ring at that of that curve corresponds to that point, the one which was omitted. Now you can, by finite repetition, you can exhaust. So you can write CK as union of finite union. Now the point is that now this yi you can put it in yi closure. So this is a this is some curve. You can always put it in some projective space and take the closure. Now what you do? You take the product of this. So let's call this okay. So then ck you can embed it into product of this c of yi bar. And then take phi of ck and take the closure. This is your this is then you prove that this is isomorphic to ck. So claim. So these are phi i's. So okay. Maybe I am a little fast here. Let me write the steps. So you put yi inside yi bar. Now you have to yes. Yeah. Okay. Here you have to use something like some proposition you need to use at some point, that if x is a abstract x is an abstract non-singular curve, and let P be a point, let P belongs to X, and Y be a projective variety such that this phi is a map from X minus P to Y, the morphism, then phi can be extended on X. Next, that is phi you can define from X to Y. So that, see here what you do, this ck is union of cyi, right? So ck you have a so this so what I am saying that this ck is union of cyi, and each cyi is inside cyi bar. And ck minus cyi is set of all finitely many points, right? Some finitely many points. So without loss of generality, I can assume that ck, I mean, if it is not 1, but if so, you can repeat the process. So cyi, so by this proposition, this cyi is inside ck, and this is a this is a projective object, projective curve. So you can extend this to cyi bar. So you need to take product, because it is just it's not just one point. The complement is not one point. You have more points, so you have to take product. So this is the idea, right? And then you prove that this image of this y, this is isomorphism. You take this phi of ck and take the closure. This is it is in some product of projective variety, and this is isomorphic to ck. So this is the very abstract way of proving. So another proof. So this proof is you can see in Hartshorne's book, but another almost similar proof, but relatively more intuitive. So first take a non-singular curve. C with function field k. Next step is that given any dVr r sitting inside k, there exists a non-singular curve which y such that OYP is R for some p. Now, by repeating this process, because this is a abstract non-singular, so you take all the local rings, so the complement will be finite. So by repeating this, we can assume that Ck is, there are Cy1 union Cyk. Not k, let me write YL. So now the point is this yi's are all non-singular curves, right? So now you glue, one can glue. Now this is a point. So glue, or it is possible to glue yi's into a curve, into a y. So when you glue the if you consider Cy, you will get Ck back, because all the dVrs are already there in the Cy's and Cy1 and Cy2. Then the next step is that this has to be projective. The y is projective curve. Because this y you got after all as a curve. So now if it is not projective, then it will be inside y bar. But if it is in y bar, but the dVrs in y already exhausted here. So now if you include, so it is sitting inside y bar. So the point which is outside y, but in y bar, that will correspond to a dVr, but the points corresponds to different dVrs. So it is not possible. So y has to be projective. Right. So that is the point, that if it is not a projective curve, it is a quasi-projective, but any quasi-projective curve you can embed it, you can take the closure in some projective space. So that is a projective curve. So there is some point missing. So but you have already exhausted all the dVr. So then this is a project. This is much more intuitive proof, but again this gluing and all these things has to be carefully written down, and essentially proofs are almost same, but this is more intuitive in the sense. Okay, so I will stop here.